Everyone wants to believe that green hydrogen projects fail because electrolyzers are immature, unreliable, or not ready for scale. That belief is comforting because it points the finger at a single piece of equipment with a clear vendor, a warranty, and a spec sheet. But when you look at why projects miss uptime targets, blow through budgets, or quietly stall after commissioning, the electrolyzer itself is rarely the root cause. The real failures happen in the systems wrapped around it. Balance of plant is where green hydrogen projects lose availability, efficiency, and money, and the industry still systematically underestimates how decisive this layer is. Electrolyzer stacks are designed to do one thing extremely well under controlled conditions: split water into hydrogen and oxygen when supplied with stable power, clean water, correct pressure, and predictable operating ranges. In test environments, they perform remarkably well. In real projects, those ideal conditions almost never exist continuously. Instead, electrolyzers are dropped into complex industrial ecosystems filled with power fluctuations, water quality variation, thermal stress, pressure cycling, control system mismatches, and maintenance constraints. None of those challenges originate in the stack itself. They live in balance of plant. Balance of plant is an unglamorous term that hides enormous complexity. It includes power electronics, transformers, rectifiers, cooling systems, water treatment, hydrogen drying and purification, compression, storage, piping, valves, sensors, safety systems, control software, and integration with the grid or behind-the-meter generation. Each subsystem looks manageable on its own. Together, they form a tightly coupled machine where small inefficiencies compound into large economic losses. One of the earliest failure points is power conditioning. Electrolyzers demand high-quality DC power, but most projects source electricity from grids or renewable assets that deliver AC power with variability, harmonics, and transient events. Rectifiers and power electronics bridge that gap, but they introduce conversion losses, heat, and failure modes of their own. When power electronics are undersized, poorly cooled, or inadequately protected, electrolyzers are forced to ramp down or trip offline. Every trip looks minor in isolation. Over a year, it destroys capacity factor assumptions. Cooling is another silent killer. Electrolyzers generate heat, and thermal stability is essential for membrane life, catalyst performance, and safe operation. Cooling systems are often treated as commodity components rather than mission-critical infrastructure. Undersized heat exchangers, fouled cooling loops, seasonal temperature swings, and water chemistry issues all degrade performance. When cooling margins shrink, electrolyzers must operate below nameplate capacity or cycle more frequently. Neither outcome shows up clearly in glossy project models, but both show up in operating losses. Water systems are similarly underestimated. Electrolyzers require ultra-pure water, yet many projects rely on raw municipal supply, surface water, or desalination outputs with variable quality. Pretreatment, deionization, polishing, and wastewater handling all sit in balance of plant. Fouling, resin degradation, pump failures, or sensor drift can quietly force derating or shutdowns. The electrolyzer is blamed for low output, but the water system is the bottleneck. Hydrogen handling introduces another layer of economic stress. Once hydrogen leaves the stack, it must be dried, purified, compressed, stored, and delivered. Each step consumes energy, adds capital cost, and introduces failure risk. Compressors are particularly problematic. They are mechanically complex, maintenance-intensive, and sensitive to contaminants and operating cycles. Compressor downtime directly translates into hydrogen production curtailment, even when the electrolyzer itself is perfectly healthy. Pressure management across the system creates further coupling. Electrolyzers prefer stable pressure regimes, while downstream storage and offtake often impose variable demands. Mismatches cause inefficiencies, cycling, and stress on seals, valves, and membranes. Over time, these stresses shorten component life and increase maintenance frequency. None of this is captured by headline electrolyzer efficiency figures. Control systems are where many projects quietly lose the plot. Electrolyzers, power electronics, compressors, and safety systems are often supplied by different vendors, each with proprietary control logic. Integration is treated as an IT task rather than a core engineering challenge. The result is slow response, conservative interlocks, nuisance trips, and limited ability to optimize operation dynamically. Operators compensate by running systems well below theoretical limits to preserve stability. Economics suffer accordingly. Availability assumptions collapse under this complexity. Project models routinely assume electrolyzer availability north of 95%, sometimes higher. In reality, balance of plant subsystems each carry their own availability penalties. When you multiply those probabilities across power conditioning, cooling, water treatment, compression, and controls, system-level availability drops sharply. A project that looks robust on paper quietly becomes marginal in practice. These losses propagate directly into hydrogen cost. Lower availability increases fixed cost per kilogram. Additional parasitic loads increase electricity consumption per kilogram. Maintenance and replacement costs rise. Revenue contracts tied to minimum delivery volumes are strained. Financing structures that assumed smooth cash flow begin to wobble. By the time developers realize what is happening, the electrolyzer is unfairly blamed for problems it did not create. This misdiagnosis shapes bad decisions. Developers chase next-generation stacks with marginal efficiency gains while ignoring system integration risk. Investors fixate on electrolyzer capex per kilowatt instead of system capex per delivered kilogram. Policymakers design incentives around stack deployment rather than operational performance. The industry keeps repeating the same pattern: impressive announcements followed by underwhelming execution. The uncomfortable truth is that green hydrogen is not an electrochemical problem anymore. It is a systems engineering and operations problem. The physics are understood. The stacks work. What fails is the orchestration of energy, fluids, heat, pressure, and control across an industrial plant operating in the real world. This is why some smaller, less publicized projects outperform larger flagship facilities. They invest heavily in conservative balance of plant design, redundancy, and operational flexibility. They accept higher upfront costs to preserve uptime and control parasitic losses. Their hydrogen may look more expensive on day one, but it is often cheaper over the life of the plant. It also explains why retrofits are so common. Projects discover after commissioning that compressors are undersized, cooling loops lack margin, or control logic is too brittle. Fixing those issues post-FID is far more expensive than designing for them up front. The cost overruns attributed to unexpected issues are usually predictable balance of plant failures that were discounted during early modeling. From a financing perspective, this matters enormously. Lenders care about reliability, predictability, and downside protection. Balance of plant uncertainty increases perceived risk, raises cost of capital, and tightens covenants. Even generous subsidies cannot compensate for a system that cannot deliver contracted hydrogen volumes consistently. This is where serious project evaluation diverges from marketing narratives. It is easy to sell electrolyzer megawatts. It is much harder to sell integrated system performance over 20 years. The projects that survive are the ones that treat balance of plant as the core asset, not a supporting cast. At this point in the video, this is where ReneEnergy points viewers to H2 Hub. Not as a pitch, but as a working environment where hydrogen projects are examined through system constraints rather than component claims. Where availability, parasitic loads, integration risk, and financing implications are treated as first-order variables. If you are evaluating or developing green hydrogen projects, this is the level of analysis required to avoid repeating the same costly mistakes. The broader implication is uncomfortable for the industry. Scaling green hydrogen is not about waiting for the perfect electrolyzer. It is about mastering industrial systems under real operating conditions. Until balance of plant is designed, financed, and operated with the same rigor as stacks, project economics will continue to disappoint. Electrolyzers do not fail nearly as often as headlines suggest. Balance of plant does. And when it does, it quietly kills project economics long before anyone admits what went wrong.